For this lesson, we're going to be taking a look at the very important topic related to the inverse of a function. So the first thing I'll do is remind you something that we talked about before we even introduced functions. We talked about relations. A relation can be thought of as a set of ordered pairs. That set of ordered pairs can be represented a number of ways. It could be represented as a list of points. It could be represented as a graph. It could be represented as an equation. But all of those things essentially define a set of ordered pairs, an x and a y, an independent variable and a dependent variable. So if we start from there, then when we talk about an inverse of a relation, essentially what we're doing is we are reversing the pairings. Another way of saying that is that we take the x and y values and we swap them. Now when we have a list of points, that's actually quite a straightforward process. For example, if I start off with my function, so this part, okay, so that would be my function. So if I asked you to determine the inverse of this, what you would do is you would go to each point and you would reverse its order. So the function says when I input 0, I get an output of 1. When I input 3, I get an output of 4. When I input 2, I get an output of -5. The inverse, we reverse those, and so now the inverse says when I input 1, I get an output of 0. When I input 4, I get an output of 3. When I input -5, I get an output of 2. So from an input and output perspective, a function and its inverse is just like reversing the direction. Now this is something I included as kind of just an aside, something to discuss briefly. It does come up in the textbook, it may appear in the homework. There is a thing called a mapping diagram. And a mapping diagram is it's essentially just another way of representing a list of points or a table of values. So what it says is for a particular input to the function, for example in this case 0, you get a particular output. That is exactly the same as saying that there is a point in this relation called 0, 1. There's also a point called 2, -5 or at 2, -5, and there is also a point at 3, 4. As you can see in this case, since the x values only appear once, or since the inputs only appear once, for each input it only produces a single result. When I put in an input of 0, I always get a result of 1. When I put an input of 2, I always get -5. An input of 3 always gives me 4. When you're dealing with a mapping diagram, to take the inverse just means reversing the arrows. So in this case, that would mean that, for example, -5 gives an output of 2, and 1 gives an output of 0, and 4 gives an output of 3. And in this case, we take a look at these x coordinates. It used to be x, y, but the whole idea of an inverse is that you swap the x and the y. So now these ones on the right are the x values, and none of these x values are repeated. So that's why I say the relation is a function and the inverse is a function. As a counterpoint to that, let's take a look at another relation. Here we have 4 producing 3, we have 7 producing -3, and we have 8 producing 3. Now you might think, oh hold on, is this actually a function because 4 and 8 produce the same value? But that's actually not a problem. 4 produces 3, 7 produces -3, and 8 produces 3. Even though these y values are duplicated, the important part here is that no x values are duplicated, and so that's why this relation is a function. So that was when we had x, y. But what happens when I reverse the dependent and independent variables, which in this case means reverse the direction of the arrows? Now I have -3 produces 7, 3 produces 4, but 3 can also produce 8. And you can see here that I have a duplication in the x coordinates. I have 3 can actually produce 2 values. It can produce a 4, but it can also produce an 8. And while that is perfectly valid for a relation, it is not a function. And so that's why, first of all, that's why in this case the inverse is not a function, and that also helps to illustrate why mapping diagrams are one way to do this. Okay, now what about from a graphical perspective? Swapping the x and y values, so if we take a point and we swap its x and y values, graphically that's equivalent to a very special kind of reflection. We've done transformations where we looked at vertical reflections and horizontal reflections, and in this case we do a very special reflection along the line or across the line y equals x. And I think I'll put that on first just so we get used to that idea. The line y equals x is a line that goes through 0, 0 and has a slope of 1. So there is the line, I'll label that. There is the line y equals x, and I put this in with a dashed line because it's not part of the graph. It's just something I'm putting on there as a reference. Now let's go ahead and actually graph this quadratic function. Now I made it fairly simple. The a value is 1, there's no k value, so really we just have to find the new vertex, which is going to be at, let's see, I think I will use 1 square per scale. So that's going to take me to -5, and then it's down by 2, so that's 1, -2, and so that's my vertex. My vertex is there. This parabola has a positive leading coefficient, so it opens up. And so from my step pattern, it's going to be over 1, up 1, over 1, up 1, 2, 3, over 1, up 1, 2, 3, 4, 5. And that will be as many as I can fit on there. If you're not comfortable or familiar with the step pattern, just go ahead and graph this with a table of values, or maybe you've learned another technique to allow you to graph a quadratic in vertex form quickly and easily. Now I do my best to draw a smooth curve in the shape of a parabola through those points as well as I can. Now let's focus on the vertex, which has coordinates -5, -2. If we swap that, then that will become -2 and then 1, 2, 3, 4, 5. So this point has gone to here, which is the point -2, -5. I've just reversed the x and y coordinates. And I can do that with any number of these points. For example, this point, and I'll label one more. This point is -4, -1. So now we have to find the point -1, -4, and that's here. This is the point -3, +2. So -3, I think I am going to have to just label these. -3, +2, that now is going to be at 2, -3, which takes us here. Similarly, if I go to this point, that's -6, -1, which now goes to -1, -6. There's -5. This point is at -7, +2, which goes to 2, -7. And let's see, can we go any higher? Actually, I missed this one, so that's at -2, +7. -2, +7. Now we have to go to 7 and -2, which takes us here. And then there'll be another point. I can actually tell this because of symmetry, but if we do it honestly, this is the point -5, 6, 7, -8, +7 goes to 7, -8. And once again, I do my best to draw my parabola through those points with a smooth curve. I didn't do great there. And now if you take a look at this blue parabola and compare it to this red parabola, this green dotted line acts like a mirror. So all of the points from this blue parabola have been reflected across to this red parabola. And you can see I'm showing you that with these purple lines. That shows the one on these edges that are closest to each other. It'll be a little awkward to do that with the other ones. I don't think I want to mess up our diagram too much by showing that, for example, way over here, if I move this down a little bit, this point way up here is going to end up way down here. And it is still, I'll try to do my best here, straight line, got a little curved at the end there. So from here all the way down to there, but it's a reflection across that green line. Here is a computer generated version of the same graph, labeling some of those points, put on with nice straight lines. And so you can see the reflection, the symmetry even better. Okay, now we've been focusing a lot on functions. Yes, all of these things are relations, but we're particularly interested in the idea of a function. Now, you can start with a function and take its inverse, and the inverse will be a relation, but there is no guarantee that the inverse itself will actually be a function. For the inverse to be a function, it has to satisfy the same conditions as any other function, and that means that each value in the range corresponds to a single value in the domain, or that's kind of an awkward way of saying it. So another way of saying it is the domain has no repeated values. Okay? If the inverse of the function, so if we start with f of x and we take the inverse, and it's also a function, meaning that the new domain has no repeated values, it's given the special designation of inverse function. And that has a special notation as well. So f of x has an inverse function, which is f to the minus 1 of x. This negative 1 is not an exponent. Just in the same way when we talk about these brackets on a function, these are not multiplying brackets. These brackets are the function brackets, which denotes the fact that this x is an input. Okay, these are not for multiplying. Well, the same thing is true here. This negative 1 is not an exponent. It is a special notation to denote that it is an inverse. You may have some experience with this already from your trigonometry, where you might have come across sine and cosine and tangent, and then the sine to the negative 1. This is not an exponent. This means the inverse sine. Sine x is a function, and sine to the negative 1 is the inverse of sine x. So here is just a regular old variable, x to the negative 1. In that case, it's an exponent, which means this is equivalent to 1 over x. Whereas f inverse of x does not equal 1 over f of x. It's an important distinction. I don't think it should cause too much confusion unless you have a situation where both of these things are coming up. Okay, now I showed you how to do this with a list of points. I showed you how to do this with a graph. What about doing this algebraically? So what we want to do is we are going to swap the x and y. And this is a bit of a trap for people who are new to inverses. I don't want to go into too much detail over it. I just want to make you aware of this now. The functions that you deal with early on in your mathematical study of functions and their inverses will often be written in terms of the generic x and y variables. So when we talk about swapping x and y, it's because x and y don't have any particular meaning other than independent and dependent. But if you're doing a question where the variables have some sort of meaning, for example, what are some letters that have meaning? T for time, D for distance, V for volume, capital T for temperature, M for mass. If you're doing a question that involves these, you don't swap the letters. All you do is you rearrange the equation. Now in this case, we don't have that situation. We have something generic. It's actually written as a function. So the first thing we want to do is make use of the relationship that our dependent variable is usually set to the output of the function. So that means that this can be rewritten as y equals 4x plus 3, the equation of a straight line. Now for the inverse, which is what we're trying to find, I'm going to swap the x and y values. And when I do that, I end up with x equals 4y plus 3. And now I'm just going to rearrange for y. So I subtract 3 from both sides, and that gives me 4y equals x minus 3. I divide both sides by 4, and I end up with y equals x minus 3 over 4. Or another way I could write this would be y equals x over 4 minus 3 over 4. The only reason I might write it this way, actually, or I might even go one step further, y equals 1/4 x minus 3 over 4. And this last one, the reason for writing it this way is because it's now once again in the form y equals mx plus b. So this tells you that this is also a straight line. And this straight line has a slope of 1/4, and it has a y-intercept of -3/4, which means it's going to look something like that. And if we performed the vertical line test on this straight line, we would see that it is a function. So because this is a function, I could actually write this as f inverse of x is equal to 1/4 x minus 3/4. Okay, now this is the same algebra that we just looked at. The original function was f of x equals. As we saw, this is an inverse function, so it gets that designation, f inverse of x, and this is the original form that I solved for. Now this is an interesting but very important consequence of a function and its inverse. And it's this word, undo. A function and its inverse undo each other. If you think of this like a machine, we have an input that comes into the machine, which essentially is where we fill the x values, and then this whole thing gives us an answer. That's our output. So we have input, and then we have output. Now the way that an inverse works, well, now we have a new input, which goes into those x's, and then we get a new output. The way that a machine like this works is that what goes into the first and then comes out, if we feed that output back into the inverse, then the thing that comes out the other end is the original input. Now, if that seems confusing, hopefully my example will clarify that for you. But what I just said there is the idea of this word undo. So let's take a look. When x equals 5, what is f of 5? So f of x is equal to 4x plus 3. So f of 5 is 4 times 5 plus 3. And that's equal to 23. Now I take that and I put it into f inverse. So I'm going to take this as my input now. So f inverse of 23, that's this one. That's going to be 23 minus 3 all divided by 4, which of course is 20 divided by 4, which is equal to 5. And 5 is where we started, and it's where we ended, because f and f inverse undo each other. So let's take a look at that with another value. What is f of negative 3? Well, that's equal to 4 times negative 3 plus 3. That's negative 12 plus 3 is negative 9. I take that negative 9 and I use it as my input, and that becomes negative 9 minus 3 all divided by 4, which is equal to negative 12 divided by 4, which of course is simply equal to negative 3 again. And so once again we find ourselves with a negative 3 here and a negative 3 here. Now you won't often have situations where this occurs, but I'm using this to illustrate the idea. F of 2.5 is 4 times 2.5 plus 3. 4 times 2.5 is 10 plus 3. That gives us 13. F inverse of 13 is equal to 13 minus 3 divided by 4, which is 10 divided by 4, which is 2.5, which is exactly what we expected. Now, it's possible, and I warned you about this before, it's possible when you take the inverse that you won't get a function. So there's the first thing. The inverse might not be a function. It is also possible to restrict the domain and force the inverse to be a function. So I'm going to illustrate that as I go through this example. So find the inverse of this. That means first of all I'm going to rewrite it in XY notation. Then I'm going to swap X and Y. It's important that you say this so that when this step occurs, so when this part occurs, it's not appearing out of nowhere. You've done something deliberate. If you go straight from this first one to the second one, I will probably think that you know what you're doing, but I won't be sure. Maybe you just got confused. Maybe you've mixed up your X's and Y's. So don't do that. Be deliberate. Tell me why you're making the step that you are. I add 6 to both sides. I end up here. I divide both sides by 3, and I end up with y squared equals x plus 6 over 3. Now I could leave it in this form, and I think I will for now. But now I'm going to take the very important step, which is in order to get this to be y equals, I have to take the square root. But because I'm taking the square root of a variable, I don't know whether I meant the plus or the minus or the positive or the negative solution, so I have to account for both of them. And this is what I end up with. I end up with the square root of x plus 6 over 3. And you might want to write this in another form. Y equals, let's see, square root, sorry, don't forget the plus or minus the square root of, this can be simplified to, or not simplified, but written another way as 1/3 x plus 2. That's if I divide both of them by 3. And just to put this into a form that we're familiar with from a transformation perspective, I'm going to factor out that 1/3, and that becomes 1/3 x plus 6. You could have gone straight from here to here as well. So this is the radical function with a horizontal stretch of 3 and a shift to the left by 6. So now that I've come up with that, you take a look. Think about if I put in a value for x here. Any number I put in here for x is going to produce both a positive value and a negative value for y. So that means, what that means is that, and let me just do an example here. Let's pick one that's going to work out nicely. What if I put in, it's going to seem odd, but you'll have to trust me. What if I set x equal to 20, let's see, 21. So in that case, y is going to be equal to plus or minus 1/3 21 plus 6 all square rooted equals plus or minus 1/3 21 plus 6 is 27 square rooted plus or minus. And now, well, what's 1/3 of 27? 1/3 of 27 is equal to 9. And so plus or minus 3. That means I have the points 21, 3 and 21, -3. Both of those points are part of this relation. And as a result, this relation is not a function. Now, I just want to see if I have a nice computer-generated graph here. I don't, so I'm just going to have to sketch this one out to illustrate what I'm talking about. So I'll make a clean page here. Y equals plus or minus the square root of 1/3 x plus 6. And I'm just going to give a very rough graph of this, or a very rough sketch. So this has been moved by 6 to the left. So there's -6. And it hasn't been reflected, so I know it's going to have that overall shape. Well, at least the plus side is going to have that overall shape. So it's going to look like that. Let's try that again. So it's going to look like half of a parabola lying on its side. The negative, so this part right here is actually y equals positive square root of 1/3 x plus 6. Then down here, we get something that looks like that, and that is the y equals negative square root 1/3 x plus 6. So this currently, now that we've drawn it, this fails quite clearly, fails the vertical line test. So how do I resolve this? Well, I could resolve this if I could just get rid of either the top branch or the bottom branch. And so the way that I do that is I restrict well, I could restrict this one, but the traditional way of doing it is you go back to the original function, which was 3x squared minus 6. So 3x squared minus 6 has a vertex down here at -6, and it looks something like that. So what I want to do now is, if I want to keep this side, so I'll call that A, this side A has positive x values. That corresponds to this side A, which has, so this side A has x's greater than 0, because this side A has y's greater than 0. And remember, a function and its inverse, we swap the x's and the y's. So to do this A option, I would set the domain of f to only be this right-hand side. So the domain of f would be x member of R, such that x is greater than, and I can leave it equal to 0 as well. If I do that, I will get rid of this left-hand branch, and by getting rid of the left-hand branch on the original, I will get rid of the bottom branch on the inverse. So that's one way I could restrict the domain of the original function to make the inverse, and so that gives me now f inverse of x. Because I restricted this domain, the inverse is now just this top half. So it's equal to the square root of 1/3 x plus 6. Okay, so let's actually see if I can get rid of my scribbles. Get rid of my scribbles, good. And now switch to another color. Well, what happens if I keep this B branch? Well, that B branch corresponds to the lower branch. So what does B have in common here? This B So if I wanted option B, I would set the domain of f to be x member of R such that x was less than or equal to 0. And by doing that, what I've done is I've created my inverse function, f inverse of x, to only be this bottom half, which is negative the square root of 1/3 x plus 6. Now, as is often the case, I've saved the most difficult part of this for last. So I may put together a more detailed or some additional examples. You'll certainly have the chance to try this, make mistakes, get your mistakes corrected as you work through this. And to help you with that, there is some assigned work, and some of these questions definitely include the idea of restricting a domain in order to produce an inverse function.